There he is.
There he is.
Hi, Al.
Hi, JJ. Hi, Jay.
Okay.
Oh,
Yeah, the webinar has started, Al. So everything you say will be broadcast to the 25 people that are tuning in. We'll wait
And
a few
recorded.
minutes. And is recorded. We'll wait a few minutes, and then Jim is going to say a few words, and then we'll turn it over to you.
Okay.
All right, we ready, Jay? Yes, we are. Welcome everybody to this week's Green Bank Observatory Community Zoom. I'm Jim Jackson. Just wanted to show quickly one of our nice results from the week. So can you see my screen?
Yeah.
So we were building a new receiver here, the ultra wideband receiver, and this is going to be used from about 700 to 4,000 megahertz, 0.7 to 4 gigahertz. And the idea here is to broaden this frequency coverage so that we can do better in our pulsar timing by getting dispersion measures. And we put it up on the telescope for our pre-commissioning. This is the first time it was on the telescope. And within a couple hours out of the gate, we observed this bright pulsar. And you can see the nice phase versus frequency waterfall plot here. Definitely detected the pulsar and have a nice pulse profile. So it's all working. We still have some technical issues to overcome, but I was very pleased that right out of the bat, we got some nice results. So this bodes well for the future of this instrument, which will be available for the next proposal call. So if you're interested in this sort of frequency coverage, it will be available to you shortly on the GBT. And just wanted to thank the team. Kudos to everyone. Everyone participated, the grounds crew, the telescope mechanics, the electronics group, the software group. Everyone had a hand in this, so congratulations. And the scientists and Ryan Lynch for spending the nights doing some of this commissioning work. So thanks team, appreciate it. And I'll hand it off to Jay.
Okay, Jim, thanks. Our speaker for today is Al Marscher, Boston University. And I'd like to remind everyone that we'll take questions in the Q&A box in the lower right at the end. And remind everyone also that this session is being recorded for later viewing. So if you miss part of it, you can always get it within a day or so from our website. Al Marscher is speaking today on peering deep into Blazar Jets. Okay, take it away, Al.
Okay. I assume that you can see my screen.
Yes.
Okay, good. Okay, so I want to say some words about how the GBT is occasionally used in VLBI in order to produce extremely high resolution images. I'm going to concentrate on millimeter wave VLBI because that's where the resolution is the highest, and that's where I've done most of my own work. Okay, so the idea is that as you go to higher frequencies, the resolution increases as the inverse of the frequency, and so you can see details that you can't see at lower frequencies or without using an interferometer, just using a single dish. Up in the upper right-hand corner here, you see what we call the core of a blazar. A blazar has a black hole that's probably somewhere around where my cursor is pointing right here, somewhat downstream. When the jet gets up to its ultimate Lorentz factor and beams its radiation the strongest, that's what we call the core. It's essentially stationary. And then flowing through the core and then down out to parsecs, kiloparsecs, and megaparsec scales in some cases is the jet. So a lot of the physics that's really interesting is going on inside this core region. You see at 43 gigahertz with a VLBA, you don't really resolve it. The beam is elongated along that direction, and so you don't really resolve the core. You need to go to higher frequencies in order to do that. Now, even though this just looks like a nearly point source, what we're really looking at here is a region like so in this cartoon of what a blazar has. A blazar is very complicated with a black hole at the center and an accretion disk around that. There's some hot electrons forming a corona. And then there's a jet that shoots out at speeds that accelerate up to Lorentz factors of 5, 10, even as high as about 50 in some cases. And then there are a lot of clouds around that give off emission lines as well. And they can form an external medium to the jet through which the jet propagates. They may be in some kind of orbiting situation where there's a combination of a wind and orbit and so on. In any case, we'd like to explore this region here. And to do that, we need to turn to the short millimeter wave VLBI. Get resolution at 86 gigahertz as high as 50 microarc seconds. So that's less than a parsec, even if for these objects that are billions of parsecs away from us, that corresponds to a distance or a size scale less than a parsec. The problem is that millimeter wave VLBI is very difficult. Of course, millimeter astronomy in general is fairly difficult. The atmosphere absorbs the waves in a time-dependent way, and also important for VLBI is it delays the microwaves that are coming in a time variable manner, and that decreases your coherence time that you have in order to integrate to try to get a stronger signal. So you need a lot of antennas across the globe to produce a high dynamic range image, but only some of those antennas end up being efficient at millimeter wavelengths. The humans haven't spent enough money to make enough antennas that are really sensitive to millimeter wavelengths to build a really good global VLBI array. And most sources are weaker at short millimeter wavelengths because the VLBI resolves out the optically thin structure. And so you're only looking at the flux that you get from the more compact structure. So at least some of the antennas need to have high sensitivity, and that implies, of course, that they should be large, like the GBT. And so the GBT can be especially helpful when you can get the time on it. This kind of shows a map of the world, showing where the various antennas of the global millimeter VLBI array, GMBA, are located. You see the familiar VLBA locations. Only 8 of the VLBA antennas observe at 86 gigahertz. The ones on the east, Hancock and St. Croix, don't observe because the water vapor is just too strong absorber at those locations. So they didn't bother putting 86 gigahertz receivers there. Greenbank, therefore, plays an important role. It's at the eastern end of the US-based antennas, and it's also closer than the other US-based antennas to the European antennas. And so, so the GBT acts as a gateway to Europe for the GMBA in a large sense, because not only is it closer to Europe, but it also it's also a very, very sensitive, a sensitive telescope. And so it can get fringes, interferometer fringes from the European antennas as well as from the VLBA. Now, the VLBA antennas are all quite small. They're for this, they're 25 meters and certainly not millimeter optimized. So they need to have some antenna that's strong enough in order to pull out the fringes as you go to sources that aren't among the strongest sources in the sky. And then the European antennas, these are long baselines. And at long baselines, you resolve out a lot of the structure, which means you have a fairly low correlated flux. And so it's very handy to have a large antenna that's not as far away from Europe as the other smaller antennas are in order to make the detections of the fringes. Okay, this shows the UV coverage that you get. This is from an observation with the GMVA in 2017 when we were able to get the GMVA to observe. This is for the fairly northern object of Blazar. Here in white, you see the UV coverage provided by the GBT, and in the green, you have the UV coverage provided by all the other antennas. And so you see that you're not too bad in the short baselines because there are a fair number of antennas in Europe, like the EROM 30-meter antenna, that are fairly sensitive. On the intermediate baselines, really the GBT fills in the intermediate baselines quite well, and that helps to get the intermediate scale structure, which is for the 86 gigahertz GMVA, would correspond to somewhere around a few tenths of a milliarc second. It also can make detections to some of the antennas that then give you the longest baselines. For example, Mauna Kea antenna out to the European antennas. That would often not be detected if you didn't have the intermediary detections of the GBT in order to get the fringes, in order to determine the delays and rates that you need in order to calibrate the data. So the GBT fills an important niche in the in a VLBI array. So I want to just review very briefly a handful of results that we've gotten from the from 86 gigahertz VLBI, including the GBT. This is a well-known BLAC object, OJ287, one of the most prominent blazars. A lot of people think that it has a binary supermassive black hole that's powering everything. In any case, from the perspective of the radio astronomer, it has a jet, has a core here, and then the jet goes out. The jet used to go out to the southwest, and now it goes up to the north-northwest, which is fairly peculiar. That's because the jets, we're sure, point almost directly at us, and so a slight change in the jet direction can make a very large apparent change in the direction on the sky. On the left, you see a 43 gigahertz image with a VLBA, and on the right is a GMVA 3mm 86 gigahertz image. And so you see the finer resolution that you get. This paper that was published in 1917 by Jeff Hodgson et al. Found that using the data, you can infer that the magnetic field in the core is greater than about 1.6 Gauss, which is quite large in a jet. And then from comparison with gamma ray, times of gamma ray flares and so on, and getting these kinds of images at multiple epochs, we can infer that the gamma ray emission is coming both from the core and from a stationary feature about 3 tenths of a milliarc second downstream from the core. More recently, 2017 observations with the GMVA combined with observations made in previous years and later the same year, we're able to make images just after there was the first outburst ever observed in this object at very high energy gamma rays, meaning somewhere greater than 0.1 tera electron volts. So these are very high energy gamma rays. And when OJ287 was detected by Cherenkov detectors on the ground, the GMVA was able to find that there was a knot coming out. And this is combining that with the 43 gigahertz VLBA observations, find that there's a knot that was coming out, appearing to move superluminally, and that knot passed through the core region right at the time when you have this very high energy detection. When you have sensitive enough antennas, you can get linear polarization in your images at 86 gigahertz. And so here's a series of half a dozen blazars whose linear polarization was measured. Here, the contours correspond to total intensity, and the color code corresponds to linearly polarized intensity. And you probably can't see it, but it has some sticks here that tell you what direction the polarization position angle is. And so we can use these kinds of polarization intensity images to figure out where there are shock waves, where if there's very low polarization, there's probably a lot of turbulence there and so on. So you can figure out a fair amount about the basic physics of what's going on inside the jets on the very compact scales that we're probing here. You can also do, combined with other frequencies, you can do Faraday rotation measurements. And that can probe the external medium, because a lot of the Faraday rotation that occurs in these sources is from a sheath of the jet or from the external medium that exists beyond the boundary of the jet. And since we're looking down at the inside the parsec scale regions, now you're looking at what the medium is like on those scales. We can also compare the position angles of the polarization with what we see in the optical emission. So we can compare we can kind of locate where the optical emission is probably coming from if we can match up unique polarization position angles. Here's another example of Faraday rotation measurements that have been made from Casadio et al. In 2019 of the Quasar CTA 102. And one thing you can do in order to increase your signal is to stack the images. So you kind of are looking at images that are stacked over multiple epochs. And so that means that you're kind of integrating over where the emission has occurred over time. And you can make the polarization images from that. And then you can make a rotation measure map. And from the rotation measure map, we find that there's a change in sign across the jet. The jet goes off in this direction to the southeast. And there's a change in sign across the jet that is what you expect to get if you have a helical magnetic field. Well, that makes the theorists very happy, because they hypothesize that helical magnetic fields are what you need in order to launch the jet and get it to accelerate up to speeds very close to the speed of light. You can also make a spectral index map. Here, when you look at the green part is more optically thick, meaning that it has an inverted spectrum. Whereas when you get to the blue here, that is optically thin. The red and the blue is optically thin. The surprise here is that it looks like it's more optically thick off to the south, which is kind of odd. You might expect that the heart of the jet would be where you get the highest optical depth. So we haven't really figured out why that's the case, but it appears that the core isn't homogeneous, isn't a uniform region. One of the objects for which Faraday rotation measurements have been made is the radio galaxy 3C84, somewhere around 70 megaparsecs away. So we're getting a really close-up view of what one of these blazars probably looks like if you get up closer to it than billions of parsecs. And here you see it's actually really a mess, very complex. What we're looking at here is probably not the most relativistic core of the jet, which is being beamed to somebody else in the universe, but we're probably looking at the less highly beamed sheath around the jet. And that's consistent with the Faraday rotation that we see. The Faraday rotation is consistent with a screen provided by the sheath of the jet. And you can find out some parameters of that, the sheath of the jet. The Faraday rotation is really high in this core of 3C84. It's almost 1 million radians per meter squared. So there's a lot of plasma here that's surrounding the jet that we're detecting with the Faraday rotation. Interesting study by Casadio et al., published in 2021 last year, is to do stacked images of BLAC and to measure its width as you move down the jet, how broad it is. You have to do that with model fitting of the VLBI data. And here's a plot of it. The blue is from the 86 gigahertz images, and the yellow here, orange is from 43 gigahertz VLBA images. You can see that within the first 4, almost 5 parsecs, the jet kind of goes out in a shape of a cone. But then when you get around 5 parsecs, now it bends in a little bit, it gets compressed a little bit. And then beyond that region, then it really expands a lot. It flares out before finally, when you get out to around 16 or so parsecs away, it finally returns to its pretty much cone shape. This is, by the way, its deprojected distance. So we've taken out the fact that the jet is pointing almost right at us. So we're projecting it as if it were 90 degrees. So this is consistent with the idea that you have a change in the pressure of the external medium that first compresses the jet, so the jet expands a little too much compared with the pressure of the external medium. And if the pressure of the external medium changes its profile, which may happen, for example, at the Bondi radius of the accretion of the interstellar medium onto the black hole, then you would expect that the expanding jet would suddenly see an interstellar medium whose pressure was constant instead of decreasing with radius, and that would cause the jet first to compress, but then it overcompresses, and then it flares out in a rarefaction wave, and so it spreads out, and it's in this region actually where the bright features that we see moving down the jet of VLBI disappear for a while, and they reappear somewhere down here. So that's all consistent with this rarefaction of the jet in response to the pressure of the external medium changing. Finally, we can use we need 86 gigahertz images in order to form a bridge between the 43 gigahertz images that my group gets every month of blazars with what's observed with the Event Horizon Telescope at 230 gigahertz. So here's an example, 3C279, a famous quasar. And here you see, you start to resolve things out in the resolve the emission in the core region. And then with the 230 gigahertz image with the Event Horizon Telescope, we now see that the core is actually elongated in a direction almost perpendicular to the jet. So just like was seen in CTA 102, it looks like the core is a fairly complex region. It's not as simple as the simple theories would have implied. So to conclude, 86 gigahertz of VLBI provides really high resolution, and that gives you the ability to probe physics of the most compact regions of relativistic jets. It also is that the higher frequency you go, the less you're bothered by opacity, and so you can look deeper into the jets for that reason as well. It's especially valuable when combined with other frequencies. So I've shown you a fair amount of comparison between 43 and 86 gigahertz and even 230 gigahertz. And so that ability to compare with other frequencies can really yield a fair amount of, quite a bit of physics. So the GBT, when it's available for GMVA observations, which understandably it hasn't so much been in recent years for financial reasons, it provides a sensitive anchor in the middle of the global array, and that produces better images, better sensitivity to polarization, and therefore better science. Thanks very much.
Thanks very much, Al, for a most interesting presentation. Let me remind everybody that they should submit questions in the Q&A box that is in the lower right of your screen. And I will read them as they arrive and get them to you, Al. Let me just ask a sort of administrative question, which is that the GMVA operates only in certain time blocks, is my understanding. And yes, so it's not really scheduled like normal VLB observations. Or did you foresee trying to change that in the future to give you a little more flexibility?
It's difficult with the GMVA because they're borrowing time from a lot of antennas similar to the GBT. And so it's done 1 week at a time, 2 times per year. The Event Horizon Telescope does about 10 days every year. for its observations. It's difficult to change because of the problems you have to get time. Because those telescopes are used for a lot of other really worthwhile scientific purposes, of course, and so they don't want to give huge amount of time to VLBI. The main thing that I would like to see would be if the GBT could give more time to the VLBA, because just adding the GBT to the VLBA really gives much better images at 86 gigahertz. The VLBA's small antennas, I observe about every 2 months or so at 86 gigahertz with the VLBA. One time you get reasonably good images, next time you don't get any good images. All you need is have bad weather at 1 or 2 sites and you're dead. And so adding the adding the GBT to the VLBA from time to time would be very helpful. Of course, the VLBA is not rich financially either, so it probably doesn't help the financial situation of the GBT to promote that. But scientifically, that would be very valuable.
I don't see any questions coming in. Let's wait another few minutes.
Hey, Jay, in the meantime, I have a question.
Oh, okay, Jim, go.
So Al, great talk. The perpendicular structure that you see the core that's perpendicular to the jet.
Yeah.
Can you speculate what that might be?
Yeah, well, there are a couple of possibilities. Let me go to so everyone knows what we're talking about. There we go. One possibility is that the jet just bends like crazy here. Another possibility is that what we're seeing is seeing a structure across the jet. And in fact, when you look at these objects for a long time, you see sometimes one side of the jet becomes brighter, then it shifts and another side of the jet becomes brighter. And if you stack the images, it looks like the jet has a nice cone shape, but you're only filling a small fraction of the cone at any given time. So that could be the case here as well, although it would make a pretty broad cone here, broader than we would have expected here. So my guess is that what's happening is that things are moving in that direction and then they curl around and go down to the southwest. So there's probably something like a cloud here or something like that that's deflecting it to go down. That's just speculation. What we really need to do is to get some time sequences of images with the Event Horizon Telescope in order to see the motions in here to see what's.
That's really cool. It's a nice result. That's really cool.
So what kind of cloud does it take to deflect a jet?
Probably, I would think an emission line cloud would do it on that, or at least a handful of emission line clouds on that scale.
Yeah, we have a question. Does the filtering of the optically thin emission affect the observed spectral indices?
Yes, you have to be very careful when you want to get the spectral index. Let me go to the slide here. This is all compact stuff, and so in here we're not resolving anything out. When you get down here, you notice that there's nothing there. That's because you don't have the sensitivity to determine the spectral index there. So you do see that effect, and you don't have to get very far downstream from the core before that effect happens in this object.
Okay, here's another question. How have the observations constrained the theoretical possibilities for the black hole converting the accretion disk inflow to the jet outflow?
Yeah, that's still a question that hasn't been answered because the best object that we have to try to answer that is M87. And as you know, the Event Horizon Telescope image of M87 sees the black hole shadow and resolves out the jet. And that's because we didn't have enough, the EHT didn't have enough of the smaller baselines of the antennas close enough to each other to image that region very well. There was you need intermediate baselines in order to do that. And there weren't sufficient number of those. So it's hoped that in the future, the EHT will be able to see that region where you see the connection between the black hole shadow and the jet and to see what's going on there, to see whether you get more emission from a region on the periphery of the shadow, indicating that it's coming off the accretion disk, or if it's coming more from the, see, from your point of view here, if the emission is coming out in a more narrow cone, then it's probably the black hole that is magnetic field immediately around the black hole that's focusing the jet.
Thanks. Well, that ends the time for this week's session. I'd like to remind everyone again that the session has been recorded and you can get it through the greenbankobservatory.org website. Please join us 2 weeks from now on April 13th, where we'll have a presentation from Karen Perez, Breakthrough Listen Search for Intelligent Life Near the Galactic Center. I look forward to seeing you then. Thanks and goodbye.
Bye, everyone.